Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our third set of notes from Chapter 17. Now, the last couple of notes, we've looked at equilibrium situations, so we had to do equilibrium math. When we're dealing with strong titrations, because that's the titration we're looking at first here, we don't have an equilibrium system, so that significantly simplifies the math. We don't have to do equilibrium. Now, we talked about titrations early in the year back in Chapter 4. And at that point in Chapter 4, what we were doing was we were using titrations to determine an unknown concentration. Like in this case, if I knew the concentration of the base in the burette, and I knew the volume of the acid in the beaker, but I didn't know its concentration, I would continue the titration, adding the NaOH until I reached the equivalence point, and now I would know the volume of the NaOH. So from those three things, our goal was to find out, okay, what's the concentration of the HCl in the beaker? So that's what we did back in Chapter 4. In this chapter, it's going to be different. We're going to know the concentration of both the acid and the base in the titration, and we're going to know their volumes. We're looking at other things. We're looking at what's the pH and what species are present in the beaker at that point. So there's 4 regions of a titration. You need to know which of the 4 you're at. You need to know what's present, and you need to know how to calculate its pH. Those are really, in the end, what we're looking at here with strong titrations. So remember, similar to what we did back in Chapter 4, it's still a titration, but the situation is going to be slightly different. Now, you can use pH meter or an indicator to determine when you're at the equivalence point, because when you get to the equivalence point, there's going to be a big swing in the pH. So we look for that big swing on a pH meter, or in the case of an indicator, we look for a color change that's somewhere in that big swing going to change colors. So when we get the color change, we know when to stop. And we want the equivalence point to equal the end point of the titration. End point is where we stop. The equivalence point is when the moles of H plus and the moles of OH minus are equal, so they've neutralized each other. We want that to be the exact same, so we need to pick an indicator that changes color when we're at the equivalence point. Now, the 4 parts of a strong titration. Now at the start, all you have is a strong acid in the beaker. We haven't added any base, we haven't done any neutralization. So this is what I call the initial acid phase, because that's all we've got is the acid. And just like what we looked at in the last chapter, if you know the concentration of the acid, then you know the concentration of the hydronium. Negative log of that would give us our pH. So in this first region, all we have is our strong floating around in water. So we've got H plus and Cl minus, those are the species present. And literally, if we know the concentration of the HCl, we know the concentration of the H plus, and we can get the pH. Now, when we start the titration, we're going to start to neutralize our acid. Now, we're before the equivalence point where they're equal, so I haven't added enough base to completely neutralize it. So I refer to this as the remaining acid, because that's what's going to happen. We had this much acid, we added a smaller number of moles of OH minus, so we neutralized some of them. We need to find out what's left. So you look at the moles of the H plus the acid gives you. And remember, that's never going to change throughout the entire titration. How much acid you have in the beaker is how much acid you've got in the beaker. But what's going to change is we're looking at different volumes of NaOH. So when we calculate our moles of OH minus, that's going to be different in the different steps. And we'll walk through all 4 of these steps in a sample problem at the end. Once we know what the H plus is, and remember, we've diluted, because anytime you mix volumes, you're diluted. So we have to find the moles of H plus left, and then we're going to divide it by the total volume. So the volume of the HCl and the volume of the NaOH added together and converted to liters. So once I know my concentration of the H plus left, now I need to do a negative log calculation to get pH. At the equivalence point, math is actually super easy, because in a strong titration, you get water and a salt that's inactive. The sodium and the chlorine that would be formed when NaOH and HCl react isn't going to affect the pH at all. And all of our H plus and OH minus have neutralized each other, so we're left with a neutral solution. We don't need to do any math to get the pH. It's going to be a pH 7. Oh, to back up 1 second, because I was just going to start to talk about what's actually in the beaker at this point. We didn't talk about that with our previous situation. When we're before the equivalence point and we haven't neutralized all of our H plus, we're still going to have some H plus left. But we now started to add NaOH minus, and all the OH minus is going to be used up because it was neutralized by the acid. So we're going to have H plus, we're going to have Na plus, and then we also had HCl. So we're going to have that anion, Cl minus, floating around inside there as well. So that's basically what is going to be in the beaker in this region. Leftover H plus, Na plus, and Cl minus. At the equivalence point, we still have the Na and the Cl minus, but we don't have any H plus left, because remember, we're at the equivalence point, H plus and OH minus have canceled each other. Now, when we go past this, instead of just water and the cation from the base and the anion from the acid, in this case Na plus and Cl minus, we're also then going to start to have OH minus left over. So past the equivalence point, we're going to look at this situation. We have OH minus in addition to our Na pluses and our Cl minuses that are there. And remember, we haven't added any more HCl, so our Cl minus in every picture is the exact same concentration, or I should say the exact same number of moles. We've added water, so it's going to be diluted, but the number of particles is going to be the same for Cl minus. But we keep adding NaOH, so notice the Na plus keeps increasing. And we used up all the H plus, so there's none of that left. All we're really going to have now is OH minus that's going to keep getting bigger, as well as the Na that's going to keep getting bigger. But the Cl minus, that's going to stay exactly what it was the whole time. Remember, the only reason we're getting more OH minus and more Na plus is because I'm continuing to add NaOH past the equivalence point. Now, at this point, as far as calculation, what we really need to do is calculate how much OH minus is left over. So the moles of H plus will be subtracted from the moles of OH minus, because OH minus moles will be bigger. That's going to give me the moles of OH minus left. Divide that by the total volume in liters, and you end up getting the OH minus concentration. And be careful, because they're still going to ask you for the pH. So notice at this point we have to do the negative log and then subtract it from 14. So it's 14 minus the POH, which would be the negative log of the OH minus. So we flip from an acid problem to a base problem after the equivalence point, in a strong acid being titrated with a strong base. Now, as far as what indicator should you use, notice in our titration curve where it's graphing the pH, at the equivalence point, there was a huge swing in pH. So honestly, we can use any indicator, like phenolphthalein changes a little bit above 7, methyl red changes color a little bit below 7. Both of those would change colors appropriately at our equivalence point. So both of them would be a good choice for an indicator. And it is a very big swing. So anything that's going to change color in the pH of somewhere around 3.5 all the way up to probably 10.5, if your color changes in that range, that would be a valid indicator to pick for this kind of titration, because the swing is so big when we're at the equivalence point. Now, like I said, it's such a big range, there's a lot of indicators that we can use. So the indicator needs to change color in the swing, but it doesn't really matter where in the swing that it happens. So we've got a lot of choices of indicators to stop at our equivalence point. Now, an actual example of a strong. So walking through and doing the calculations we just talked about. So we know the concentration of the acid and base, and we know the volume of the acid in the beaker, and that's never going to change. And what we're going to be doing is adding different amounts of NaOH. So in region 0, this reaction hasn't happened yet because we haven't added any NaOH. We just have HCl floating around. So that calculation is going to be very different from the others. But just as a general start to this problem, we can do a stoichiometry titration style dimensional analysis to predict at what point we're going to get to the equivalence point. And that's kind of nice to know going into the problem. So if we know we have 50 milliliters of 0.1 molar HCl, and we know it's a 1-to-1 stoichiometry, and we know what the concentration of the base is, we can actually do a stoichiometric prediction to see how much NaOH we're going to need to get to the equivalence point. And notice it's right at 50.0. So when you look at our 4 numbers, A is before the titration begins, B is before the equivalence point, C is at the equivalence point, and D is after the equivalence point. So we're going to practice all 4 of the calculations we looked at. Now, one of the useful things at the beginning of the problem is to sometimes know what's the equivalence point volume, so you can quickly see where you're at. But technically, you can get away with not knowing, because that's the first thing we're going to do is establish H plus and OH minus, and you can compare those 2 mole amounts to see where you're at. And we'll look at that as we go. Now, during the titration, and remember this is during, so this is regions 2 through 4, what we really need to know is how many moles of H plus, how many moles of OH minus, and what's the total volume in liters. Those are really the 3 things we have to find so we can answer the question. And remember, finding moles is liters volume times molarity, and finding total volume is just adding. And since we're going to be in milliliters and we need liters, you have to add the acid plus the base volume and divide by 1,000. So remember, we're going to be doing that math in every single region, technically except for region 3, but we'll at least do part of that math in region 3 even. So the amount of H plus in the flask, remember, is always going to be the same because we're just adding NaOH to it. So the number of moles of H plus would be calculated using this equation, and that's never going to change at any point in the titration. That's always how much moles of H plus is in the beaker. But over time, we're going to start to neutralize that. And while its starting value is not going to change, how much we actually have left is going to change as we go through the titration. But that's what we've got at time 0. But honestly, at time 0, we don't really need to know that. All we need to know is we've got a strong acid. The concentration of a strong monoprotic acid equals the concentration of the H3O plus. So the negative log of that would give us our pH. So at 0 milliliters, I know in my titration curve, I'm going to have 1 basically as my pH value. Now, region 2. Here's where you have to start calculating your H plus and OH minus for every step and know what your total volume is, because now we've mixed solutions. And we've not only diluted because we added volume of water, but we've also neutralized. So this is where that neutralization reaction comes into play. And remember, it's a nice simple 1-to-1 stoichiometry. So we use up an H plus for every OH minus we have, which makes the math very, very simple. So first we need to know the moles of OH minus, because remember, we already calculated the moles of H plus at the beginning. And now we need to calculate how much OH minus moles we've added, because neutralizations are particles. We have to be at a particle level here, or moles of particles. And remember, OH minus is smaller, so when I subtract, I'm going to have none left. And this is how much H plus I'm going to have left. So to calculate the pH, I need to take that number of moles and divide it by my new volume in liters, because remember, I've added 50 milliliters and 49 milliliters to get 99 milliliters. That would give me the concentration of the H plus, and then take the negative log of that, and that would give us the pH. So when we're all the way over at 49 milliliters, we've only gone from 1 to 3. And at that point, we get to our third region. Remember, 50 milliliters was when the H plus and the OH minus were equal, and I knew that because I made that prediction at the beginning. So I already did that calculation using stoichiometry, but if we calculated the moles of NaOH like we have in the previous section, notice we end up with the exact same thing as the H plus. So even if we didn't do the stoichiometry, we can still see when we're at the equivalence point, because it's the point at which the mole amounts are equal. They will have perfectly neutralized, and I don't need to do any math to get the pH, because I have water and a neutral salt, 2 ions that come from Strong's. They're not going to affect the pH, so I'm always going to have a pH of 7 at region 3. And then after this, as I add more, now I'm going to have leftover OH minus, not leftover H plus. So literally my job is to do the same thing, find out how many moles of OH minus I'm adding, but now I'm going to subtract it OH minus minus H plus to see how much OH minus is left over. And the big thing to remember here is we're getting OH minus after we divide by the total volume in liters. So when we do the negative log, we have to subtract it from 14 to get our pH. So going from 49 milliliters to 51 milliliters, we had a massive change of pH from 3 all the way up to 11. And that's why I say at the equivalence point, there is going to be a big swing. And that is strong, strong titration, I believe. Yep, because that's when the weak strong.